Hello and welcome to another one of D's ADD videos. Today we're going to be discussing another example of linear transformations. In this case it's going to be a R3 to R2, forgot that little R right there, sorry about that. Meaning we're going from three-dimensional space in our domain to two-dimensional space in our codomain. And the specific transformation we're going to look at is we're going to have the three variables x, y, z, and then the new space V, our codomain, our x values are obtained by taking the original y value times the original z value, and the y values are obtained by just taking the x value there. Alright? Some of you like working with a, b's, and c's and not x1s, y1s, and z1s, so I'll try that for this one. So here's the initial question when we're doing vector or linear transformation addition. Sorry. Just to see if it's preserved under addition. So the question is that when I take two such vectors and apply the transformation, what do I get? So this first step is just doing vector addition right here. We're adding the x components and the y components of these two vectors and the z components. And when you do so, you get this vector there. And then if you apply the transformation, meaning y times z, and then the x in the y spot, you're going to end up with this using this y and this z. And then your x values right there. So then if we FOIL out, we get what this transformation here ends up being is this right there. And what we want to do is we want to check to see if that equals this over here. So I'll give you a second to catch up and write all this down. You do have the rewind capabilities with a video and the pause ability. So after we do that, what we need to do is see if we get the same thing when we just do the individual transformations first and then add them. So when we do that, if I take this y, this z, multiply them together to get that, and then the x value goes here because of our transformation. Same concept there. Then if we do vector addition, and then add the x's and add the y's, you get this right here. And then when you compare the two, you see that they're not equal, right? The individual transformations added together that we just did right there gave us this answer, and the one above, when we did the transformation sum first and then the transformation, we didn't get the same thing. So that tells you that we are not preserved under addition. So right away you know it's not a linear transformation because both conditions have to be met. But just in case you did the other one, let's go ahead and do that. Okay, so not preserved under addition, mainly because this component right here does not equal that component there. So now let's look at multiplication. So basically we have the scalar multiple through. Does that equal each one plugged in for this transformation? So if we apply the transformation with the scalar plugged in initially, we get ky times kz, comma, kx, applying the transformation. Then when you simplify that, you get k squared yz times kx. Factoring out the k, you should notice right away that that k right there looks strange, right? So what we got to do now is compare that to what you have, and it should already be apparent without even me writing it. Does that equal the transformation with the k times the x, y, z? And sure enough, it does not, because that would be what? Let's do that in red. That would be k y z times kx. And these two do not equal each other because of this extra k right there. So that would tell you that what? We're not preserved under multiplication. Either way, it's not a linear transformation. Now make sure you don't forget to write the last step, the most important step. Some people do all this work and say it's not preserved under one or the other, but then forget to say therefore not a linear transformation. Okay, so make sure you check out the matrix examples. Doesn't necessarily have to be a relationship or a function like that. It could be a derivative, or it could be other things that are linear transformations, just as long as the patterns of addition are preserved and the patterns of scalar multiplication are preserved. Alright, I hope I've cleared up any confusion that you might have, and again, practice, 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 and check out the other example videos. Thank you and have a nice day.